aging is likely to be the loss of epigenetic information in yeast going back 20 years ago, but we really had no sense that this was true in terms of cause and effect in mammals. And so we took a mouse, we engineered a mouse strain where we could disrupt the epigenome. And if we were right, well, let's start with if we were wrong. Lots of bad things could have happened. The mouse could have died, the mice could have gotten contracted cancer, and it's possible nothing happened if you disrupt the epigenome, no big deal. And I think there's, most people would have said there's a 1 in 1,000 chance that you'll get what you're looking for, which is aging. But that's what we got. We got aging in these mice, which was a pretty good result. And when you surprise yourself how good it looks, it's usually you're on the right track. But what that said was we had to think differently about our wheel of fortune, these hallmarks of aging. Now, I'm not coming out and saying the hallmarks are wrong, not by any means. But what I'm saying is that just having a laundry list of problems doesn't explain why things occur in the first place. So it's not a full unified theory. It's really what every field is hoping for, is not just a list, but a real cause. You could distill down aging into an equation if this information theory is right. But what's exciting is that this mouse where we disrupted the epigenome, it didn't just get to look old, and it didn't just get diseases of aging. These hallmarks of aging also occurred. So loss of mitochondria, mitochondrial function, loss of stem cells, inflammation, senescent cells. All of these hallmarks occurred. So that tells you likely that the epigenome is what I would say is upstream, is the dam upstream, and these others are tributaries, which is pretty exciting. But what that also meant was that the field that was really just focusing on longevity genes to slow one or more of these hallmarks. That's what we've been doing for the last 20 years. My lab certainly is involved in that through activation of sirtuins. What it also said was that if epigenetic change and noise is the upstream cause, then if we address that and reverse it, all these other symptoms of aging, hallmarks, and diseases should either be prevented or, if we're really lucky, can be reversed. And so we didn't know if there was an observer, which you can also we refer to as the backup hard drive of the youthful information in the cell. We didn't know there was such a thing. But in 2014, I became very interested in Claude Shannon's work, and I read all of it, some of the most beautiful papers I've ever read. And I was trying to find the observer, and so we were giving cells a whole bunch of factors that we thought might reverse their age by tapping into the observer. We didn't know where the observer was, if it existed. We had a breakthrough about 2 years ago where we put in a set of 3 genes, and it looked like we managed to find the zip code of the observer, and the observer woke up and reset the age of the cells. And when we did it in the mouse, it reset the age of the mouse. And old mice that lost their vision got their complete vision back again. I've gone from a lab with just one person in my lab working on reprogramming to now probably most of the people in my lab working on it. So we're working really hard. One thing that's interesting is so we can measure DNA methylation age of the animal and the cells, the neurons in the eye. And we could see that these Yamanaka factors, the way we deliver them and the combination doesn't cause cancer, doesn't have any untoward effects in the animals, even if we look very carefully histologically, which is great news. That's hot off the press. But the reason that I'm excited about the DNA methylation clock is because I think that it's a very deep layer of aging. We can change superficial things. For example, we can go for a run today and change some transcription factors and change gene expression, but that's not permanent. That's just going to change temporarily your cells, and they'll take up more glucose, etc. There's a deeper level where we've been working on some epigenetic factors such as sirtuins and trying to activate them. But even then, if you stop giving these molecules that activate the system, the animal will revert back to being healthier and maybe longer term longer lived, but it's not that you've really reset the clock. The deep layer is the actual information that tells you your age, and it's how cells really understand what type of cell they are and how old they are. Okay? And we think that this is partly driven by DNA methylation, but we thought up until our paper that the methylation age, these chemical marks on the DNA, were an indicator of biological age. They were just basically the crust on the genome, the plaque on your teeth, so to speak. Plaque doesn't do much, right? It's just accumulating. Same we thought about the methyls. But what we decided to do was to knock down or knock out, we've done it both ways, a set of genes called TETs, T-E-T, and there are 3 of them. And if we got rid of at least number 1 or number 2, we haven't studied 3 yet, we didn't get the vision restoration and we didn't get the clock reversal. So what does that say? These enzymes are the enzymes that remove the methyl off the DNA, the PIC that removes the plaque off your teeth. If you don't have plaque remover, you don't get shiny teeth anymore and you don't get to look younger. Your dentist can't do a good job. So that's what what the results are telling us, is that part of the reset of the clock, it's not just an indicator of age, as if you move a clock hand and nothing really changes. But what it says is that perhaps you move the clock back and it actually changes time. But to move that clock back, you need to remove the DNA methylation. Now, of course, that's not sufficient. We don't think. We're testing whether it is sufficient, but we do know it's necessary for the age to go back. Now, does this prove the existence of an observer? And one of the experiments that convinced me was the following. So we can look at all the patterns of gene expression, which genes run and off in these neurons, and can look at every gene in the cells. And what we found was that genes that go down a little bit with aging, in terms of getting switched off, when we reprogram those cells, they go back up to normal, but just the right amount to where they were when they were young. If a gene goes all the way down when the animal's old, it goes way up when we reprogram them. Remember, we're not telling them which genes to turn on and off and at what level. The cell somehow knows that for the whole program. And so it's not mimicking an age reset. It's actually fully resetting the program at the gene expression level, at one level, and the very deep level, which is the DNA methylation level. Now, there are a lot of things we don't know. We don't know how many times can you reset. Is it once, which we've done, or is it 100 times? And we don't know what tells the TET enzymes which methyls to remove and which ones to keep. Now, unlike our teeth and plaque, with our teeth, we can get rid of all the plaque and there's no problem. If we remove all the plaque off our DNA, all the methyls, our cells will lose their identity completely, and we would become the biggest pool of stem cells, basically be a tumor. That's not what's happening. We don't have mice that have tumors in their eyes. We have mice that can see again. So it's as though, now another analogy would be a pianist playing 20,000 different genes. And that pianist makes some mistakes, but now we bring in a new pianist and they can play just the right notes. And we're not stripping all the notes off. We're not ripping the piano off or the keys off the piano. So the observer, in my mind, has to exist. But exactly how the observer knows which of those changes to make to go back to restore the gene expression, we don't know that at all. I think there's probably a Nobel Prize up for grabs if someone wants to figure that out. Now, we're giving it our best shot. But in terms of philosophically, where would this lie? Where would the observer be? So it could be, and I'll tell you some of my best ideas, it could be a new type of DNA modification, so it's on the genome. It could be a protein that's binding to the genome when we're young that stays there for 80 years. Or it could be some quantum state that I hope not, because that's going to take us a little longer to figure out, but it's quite possible.